You are already dying. Not eventually. Not someday. Right now, as you sit here, your cells are hemorrhaging usable energy into the void, producing heat that dissolves into the air around you and never comes back. You are, at this exact moment, participating in the single most terrifying process in all of physics. And you didn't even notice. But here's what's worse. The universe is doing the exact same thing. And it's losing. Take a breath. Just one. Feel your chest rise. Feel the air move through you. Feel the faint warmth of your own body radiating outward into the room. That warmth is gone now. You can't get it back. The universe can't get it back. And somewhere in that simple, invisible, unremarkable breath is the proof of everything that is coming. For you, for every star in the sky, for every galaxy, for every last atom of matter that has ever existed or will ever exist anywhere in the cosmos. The end is not a theory, it is a law. And right now, without your permission, without any announcement, without any way to stop it, it is happening. Look around you. Look at the light in the room. Look at the objects surrounding you, the walls, the floor, the screen you are watching this on. Everything you can see, everything you can touch, every person you have ever loved, every civilization that has ever risen and fallen across the entire surface of this planet, every mountain and ocean and burning star in the sky, all of it is moving right now toward a single destination, a destination so cold, so empty, so absolute that the word death isn't even close to powerful enough to describe it. Scientists call it the heat death of the universe. And based on the latest calculations released just recently by some of the most rigorous physicists alive, it may be arriving far sooner than anyone previously imagined. Sooner, of course, is a relative term when you are talking about the end of everything, but the fact that we just revised the timeline, that we just looked at the math, and realized we were off by an almost incomprehensible margin, that should tell you something. It should tell you that we are still figuring this out, that the universe is still surprising us, and that some of the surprises are not comforting. Let's start at the beginning. Not the beginning of this story, the beginning of everything. 13.8 billion years ago, the universe did not exist. There was no space. There was no time. There was nothing. And then there was something, erupting outward in every direction simultaneously, creating space itself as it went, filling the void with fire and light and the raw materials of everything that would ever come after. In those first seconds, the universe was the hottest, densest, most chaotic place imaginable. Energy was everywhere. Matter was everywhere. The cosmos was alive in a way it will never be again. That moment, that impossible, singular, unrepeatable moment, was the peak. Everything since then has been the fall. Because here is what physics tells us, and what nobody warned you about in school. The universe doesn't just exist. It evolves. It changes. It moves in one direction and one direction only, driven by a law so fundamental that it governs everything from the breath you just took to the death of the last star in the sky. That law is the second law of thermodynamics, and it says, with absolute certainty, that the total disorder of a closed system always increases over time. Always. Without exception, no matter what. The universe is a closed system, and disorder, what physicists call entropy, has been rising since the first microsecond of creation. Every time energy moves, every time something burns, every time you think a thought, or your heart beats, or a star explodes somewhere in a galaxy you will never see, entropy goes up. Usable energy converts to unusable heat. Order dissolves into chaos. And that process, that slow, relentless, mathematically inevitable process, is the mechanism of the end. But here's where it gets strange, because it's not just entropy that's killing the universe. Something else is involved. Something we discovered only in 1998. Something so bizarre that the scientists who found it spent months assuming they had made a mistake. Something that, even now, after decades of study and billions of dollars of telescope time, we still cannot explain. And it is doing something terrifying to the universe right now, at this very moment, as you sit here. Cast your mind outward. Outward past the room, past the building, past the city, past the horizon of the Earth. Outward past the moon hanging in the dark, past Mars with its ancient frozen riverbeds, past the gas giants swirling in their cold, distant orbits, past the edge of our solar system, past the vast interstellar void, into the sprawling, luminous architecture of our galaxy. 400 billion stars, wheeling in slow formation, around a black hole 4 million times the mass of our Sun. And then outward past even that, past the Milky Way, into the cosmic neighborhood of galaxies. Andromeda, the Triangulum Galaxy, the Local Group, dozens of galaxies all loosely gravitationally bound, all moving together through the larger fabric of space. And then outward past even those, into the deep cosmic web, into the supercluster filaments, into the regions where galaxies exist in numbers your mind cannot process. Hundreds of billions of them, each containing hundreds of billions of stars, stretching in every direction to the edge of what we can possibly observe. And every single one of those galaxies, every one, is moving away from us. Not because they are traveling through space, because space itself is stretching, growing, expanding. The fabric of the universe, the literal geometry of reality, is being pulled apart like dough, and every point in it is moving away from every other point, not because anything is pushing them, but because the medium itself is inflating. We knew this. Edwin Hubble proved it in the 1920s. The universe is expanding. Fine. Expected, even, if the Big Bang set everything in motion. The natural assumption was that gravity would eventually slow this expansion. That all that matter pulling on all that other matter would, over time, apply the brakes. That the universe would either coast to a gentle halt or collapse back inward. Physics made sense. And then, 1998 arrived. And two teams of astronomers working independently, doing the most careful measurements they could manage, found something that should have been impossible. They were using supernovae, exploding stars, as cosmic distance markers. Type 1. A supernovae always explode with roughly the same intrinsic brightness, which means by measuring how bright they appear from here, you can calculate how far away they are. And by measuring the redshift of their light, how much the wavelength has been stretched by the expansion of the universe, you can calculate how fast space was expanding when that light was emitted. The logic was elegant. The goal was to measure the rate of cosmic slowdown, to quantify exactly how much gravity was applying the brakes. But the brakes weren't working. The supernovae in the distant universe were dimmer than they should have been. Not brighter, dimmer. Which meant they were farther away than they should have been. Which meant the universe, far from slowing down, was accelerating, speeding up, expanding faster than before. Saul Perlmutter, Adam Rees, Brian Schmidt, 3 astronomers, 2 teams, 1 universe-shattering result. They won the Nobel Prize in Physics in 2011. But the prize didn't explain the thing they'd found. Because to explain acceleration, you need a force. Something that counteracts gravity. Something that pushes matter apart instead of pulling it together. Something embedded in the fabric of space itself, invisible, undetectable by any instrument we have, present everywhere and in everything, and apparently strengthening over time. They called it dark energy, and we have no idea what it is. None. After more than 25 years of research, after satellites and telescopes and particle colliders and theoretical frameworks and arguments between the most brilliant minds in physics, we still cannot tell you what dark energy actually is. We know it exists because we can measure its effects. We know it comprises roughly 70% of everything in the cosmos, more than all the matter and radiation in the universe combined. And we know it is winning. Right now, as you sit in this room, dark energy is stretching the space between the Milky Way and every galaxy beyond our local group. The galaxies that humanity has spent centuries naming, cataloging, photographing, marveling at, the Virgo cluster, the Coma cluster, the Great Wall of Galaxies 60 million light-years away, are receding. Every second, the space between us and them grows, and at some point, in the distant but inevitable future, they will be moving away from us faster than the speed of light. Not because they're traveling faster than light, but because the space between us will be expanding faster than light can cross it. And then their light will never reach us again. They will vanish, not explode, not fade, just vanish. Blink out of our observable universe forever, as if they had never existed. From the perspective of anything living in the far future of our galaxy, the universe will appear to contain only our local group. The rest, billions of galaxies, trillions of stars, will simply be gone, erased by expansion. And the future inhabitants, if any exist, will have no way to know they ever existed. No fossil, no echo, no evidence. An entire chapter of cosmic history, deleted. That will happen in roughly 100 billion years. 100 billion years from now, the observable universe shrinks to our local group and nothing else. That's the first step. But here's what keeps physicists awake at night. 100 billion years isn't very long in cosmic terms. The universe has already been running for 13.8 billion years. 100 billion is only about 7 times that. On the scale of what comes next, 100 billion years is practically tomorrow. And what comes next is a sequence of events so drawn out, so vast, so incomprehensibly prolonged, that our entire written history, 10,000 years of civilization, art, war, language, love, mathematics, music, would occupy less than a single electron's width on the timeline. What comes next is the long dying. Think about stars, not abstractly. Think about the sun. Think about the light coming through your window, the warmth on your skin on a summer afternoon, the way everything living on this planet, every blade of grass, every reef, every breathing thing, is powered by that steady, ancient nuclear fire, burning 93 million miles away. That fire is a fusion reaction. Hydrogen atoms being crushed by gravity until they fuse into helium, releasing energy. The Sun has been doing this for about 4.5 billion years. It will continue doing it for roughly another 5 billion. And then it will be done. When the hydrogen runs out, the Sun will swell into a red giant, swallowing the inner planets, boiling the oceans of Earth, sterilizing whatever remains of whatever we built. Then it will shed its outer layers and collapse into a white dwarf, a dense, hot, slowly cooling remnant about the size of Earth. No more fusion, no more light, just a fading ember cooling over billions and billions of years. And across the universe, other stars are doing the same thing. The most massive stars burn out in millions of years. Medium stars like the Sun, in billions. The smallest, most fuel-efficient stars, the red dwarfs, can burn for trillions of years. But even they run out. And when they do, they leave behind white dwarfs, cooling, dimming, fading. Somewhere around 1 trillion years from now, the last star-forming regions will go cold. The gas and dust that galaxies need to make new stars will be exhausted. The last red dwarf will have settled into its final slow burn, and no new fires will be lit anywhere in the universe. The era of stars, the Stelliferous Era, physicists call it, the age of light, will be over. Think about what that means. The universe as you know it, as every living thing that has ever existed, has always known it. Lit by stars, warmed by stars, powered by stars, giving rise to planets and life and thought because of stars. That universe will be gone, replaced by darkness. The galaxies will still be there, technically, but they will be populated only by dead stars, failed stars, black holes, and cold, dark remnants drifting in silence. No light, no warmth, no energy cascading down through ecosystems. Just objects orbiting each other in the dark. And this is where it gets worse, because those white dwarfs, those dead stellar remnants cooling in the darkness, will not last forever either. White dwarfs are made primarily of carbon and oxygen. For a long time, physicists assumed they would simply cool indefinitely, eventually crystallizing into what would essentially be giant cosmic diamonds. Unimaginably cold, unimaginably dark, just sitting there for eternity. Harmless relics. But that's not what happens. Here's where a discovery from just recently changes everything we thought we knew. Heino Falke and his team at Radboud University, researchers who spend their professional lives thinking about the death of the universe in precise mathematical terms, recalculated the fate of white dwarfs. And what they found was that white dwarfs don't just cool and sit there forever. They evaporate, not quickly, not in any way that resembles what we think of as evaporation, but through a quantum mechanical process, through the slow, bizarre, probability-driven behavior of subatomic particles, white dwarfs gradually lose mass. Particle by particle, impossibly slowly, they decay. They dissolve. They eventually disappear. The timescale? 10 to the power of 78 years. Write that out. 10 followed by 78 zeros. A number so large that comparing it to the current age of the universe is like comparing the entire age of the universe to the smallest unit of time we can measure. It is not a number that human minds can actually hold. It is a number we can only acknowledge. But here's the thing that makes it disturbing. Previous estimates put the end of white dwarfs at 10 to the power of 1100 years. That's a 1 followed by 1100 zeros. Compared to that, 10 to the 78 is nothing. It is millions of times shorter. The universe doesn't just end sooner than we thought. It ends astronomically sooner. And we only just figured this out. Which raises the question, what else are we wrong about? What other deadlines are approaching faster than we realize? And here's the part nobody wants to think about. There's another possible ending, an ending that doesn't follow the slow, cold, orderly progression we've been describing. An ending that could arrive not in trillions of years, not in Googles of years, but at literally any moment. Right now, while you're watching this, while you're breathing, physicists call it false vacuum decay. And understanding it requires understanding something about the nature of reality that is deeply, genuinely unsettling. Think of energy like a landscape of hills and valleys. Systems naturally settle into the lowest available valley, the state of lowest energy. This is why a ball rolls downhill, why water flows to the sea, why physical systems seek stability. But here's the problem. What if the valley you're sitting in isn't actually the lowest point? What if there's a lower valley somewhere else, separated from you by a hill? In the everyday world, you'd need to climb the hill to get there. But in quantum mechanics, particles can tunnel through barriers. They don't need to go over the hill. They can appear on the other side. Now apply this to the universe itself. Physicists have strong theoretical reasons to believe that the universe may exist in what they call a false vacuum, a state that appears stable, that has been stable for 13.8 billion years, but that is not actually the true ground state of the underlying physics. The true vacuum, the genuine lowest energy state, might be something entirely different. And if a bubble of true vacuum ever nucleated somewhere in the universe, a quantum fluctuation that triggered the transition, that bubble would expand outward at the speed of light. The speed of light. Which means you would have no warning. None. The bubble would be racing toward you at the maximum possible speed anything can travel, and the light from its approach would arrive at the exact same moment it did. You would not see it coming. You would not have a chance to react or think or say anything or feel anything. One instant you would exist. The laws of physics would be exactly as you've always known them. The next instant, which would not even feel like an instant, because there would be no subjective experience of transition, everything would be rewritten, not destroyed in the conventional sense, changed. The laws of physics themselves, the constants that determine how atoms hold together, how forces interact, how matter behaves, would be different. And in those different laws, the matter that makes up your body, the matter that makes up the planet, the matter that makes up the stars, would not be stable. It would dissolve, instantly, without pain, because pain requires a nervous system, and a nervous system requires atoms that obey the current laws of physics, which they no longer would. The universe ends, not with a whimper, not with a bang, with an edit. The probability of this happening is thought to be extraordinarily low. And the universe has, after all, lasted 13.8 billion years without it occurring. But extraordinarily low is not zero. And in a universe that may be infinite in extent, extraordinarily low probability events don't just happen eventually. They happen everywhere, all the time, continuously, as long as there is time for them to occur. We have no way to rule it out. We have no way to detect it coming. And we have no way to prevent it. The end could be now. It is almost certainly not now. But it could be. Hold that thought, because it's about to collide with something even more disturbing. Remember dark energy? The mysterious force driving the acceleration of the universe? The thing that makes up 70% of all the energy in the cosmos, and that we cannot explain? Here's what we've been assuming. We've been assuming it's constant. That the repulsive push of dark energy is a fixed property of space itself, the same everywhere and always. Einstein called it the cosmological constant, and the simplest models of dark energy treat it as exactly that. A number. Unchanging. Eternal. But what if it isn't? The Dark Energy Spectroscopic Instrument, DESI, is a survey telescope that has been mapping the universe with extraordinary precision, tracking how the structure of the cosmic web has changed over billions of years, essentially reading the history of dark energy's influence written into the distribution of galaxies across time. And the early results are raising eyebrows, because they suggest dark energy might not be constant. It might be changing, weakening, fading over time. If that's true, the implications are profound. A weakening dark energy means the universe's acceleration might slow. And if dark energy weakens enough, gravity could reassert itself. The expansion could stop. And then, reversal. The galaxies would stop moving apart and begin falling back together. Space itself would contract. The cosmic web would crumple inward, galaxies merging, temperatures rising, density skyrocketing, until everything in the universe converged on a single, incomprehensibly hot, incomprehensibly dense point. The Big Crunch. Not a cold, quiet, infinitely prolonged death. A violent, catastrophic, spectacular collapse of everything into a singularity. The entire universe falling into itself like a star, but 1 trillion times more extreme. We don't know which ending awaits us. We don't even know if we're asking the right questions yet. The data is new. The conclusions are preliminary. But the fact that the data exists, the DESI is out there right now, staring at the universe, measuring something that might be changing, tells you we are not done being surprised. The universe still has secrets, and some of those secrets have timelines attached to them. But let's go back to the most likely scenario, the one that the majority of cosmological evidence still points to: the heat death, the big freeze. Because even within that scenario, the sequence of events between now and the end is stranger than any science fiction. We talked about the death of stars. Now let's talk about what comes after. After the last white dwarf has evaporated, after 10 to the 78 years have passed, what remains? Black holes. Black holes form when massive stars die, collapsing inward under their own gravity until they create a point of infinite density, a singularity surrounded by a region of space where gravity is so strong that not even light can escape. We once thought black holes were, essentially, eternal. Gravity traps everything. Nothing gets out. They just sit there forever, getting larger as they devour surrounding matter. Then, Stephen Hawking came along. In 1974, Hawking derived a result so startling that many physicists initially refused to believe it. Using a combination of quantum mechanics and general relativity, Two theories that are not supposed to work together, two frameworks that actively contradict each other at the mathematical foundations. He showed that black holes are not eternal. They radiate. Slowly, incredibly slowly, but they radiate. The mechanism is deeply strange. Quantum mechanics tells us that empty space is not actually empty. It seethes with virtual particles, pairs of particles, and antiparticles constantly flickering into existence and annihilating each other. Too brief to be detected. A foam of probability at the smallest scales of reality. Near the event horizon of a black hole, something peculiar happens. A pair of virtual particles forms, and before they can annihilate, one falls into the black hole. The other escapes. The escaping particle carries energy. The black hole, having effectively lent energy to the pair, loses mass. Infinitesimally, imperceptibly, but over time, enormous, incomprehensible time, this Hawking radiation drains the black hole. Slowly at first, then faster as the black hole shrinks, until, in the final moments, it erupts in a burst of high-energy radiation and vanishes. Gone. A black hole that took millions or billions of years to form, evaporating in a final flash. The largest supermassive black holes, the behemoths at the centers of galaxies, the ones that dwarf entire star systems, take up to 10 to the power of 100 years to evaporate. That's a Google years. 10 to the 100. 10 to the 100 years. Even 10 to the 78 years, the death of the last white dwarf, will have passed long before the last supermassive black hole is gone. And when it does go, when that final particle of radiation dissipates from the last black hole's evaporation, something historic will have happened. There will be no more objects in the universe, no more matter bound into structures, only particles, scattered, drifting, separated by distances so vast that interactions between them are extraordinarily unlikely on any humanly comprehensible timescale. And faint electromagnetic radiation, the cooling afterglow of all that has come before, spreading thinner and thinner through an expanding void. The universe will be cold. Incredibly, impossibly, absolutely cold. Close to absolute zero, the theoretical minimum temperature minus 273.15 degrees Celsius. Not quite absolute zero, because Hawking radiation has a temperature, and faint radiation will still exist. But close. Colder than anything in the universe today. Colder than the interstellar void, which is already barely above 3 degrees Kelvin. The final universe will make that seem like a roaring furnace. And it will be dark. Not the darkness you've experienced, the darkness of a power cut or a cave or a night without streetlights. This will be a darkness with no stars, no galaxies, no firelight, no chemical reactions producing light. No biological processes producing bioluminescence. No nuclear reactions, no plasma, no hot gas. Just cold, scattered particles in cold, expanding, empty space. And in that universe, here is the most haunting part. The concept of time itself becomes almost meaningless. Time, as we experience it, as we measure it, as we build our lives around, is fundamentally connected to change. We measure time by watching things change. The movement of the sun, the oscillation of atoms in an atomic clock, the decay of radioactive elements. Time is the dimension along which change happens, but in a universe where nothing changes, where particles drift apart at such distances that they never interact, where temperatures are so uniform that no energy gradients exist, where entropy has reached its maximum possible value. What is time? There is no clock left to tick. There is no process left to mark the passage of moments. The universe does not end. It persists, frozen, complete, unchanging. A perfect, eternal, dead equilibrium. Physicists call this state thermodynamic equilibrium. The final state. The state where the second law of thermodynamics has extracted every last ounce of order from the universe and converted it all to maximum entropy. No light, no heat, no movement, no thought, no life, no information, no story, nothing but scattered particles in an eternal dark void, with no way for anything to ever be different again. That is the heat death. That is where we are going. And here is something that should stop you cold. The same process, the same thermodynamic increase in entropy, the same irreversible conversion of usable energy into unusable heat, is what is happening inside your body right now. Your cells are constantly doing work. Chemical reactions, electrical signals, mechanical motion, the synthesis of proteins, the pumping of ions across membranes. All of this requires energy. All of it produces waste heat. All of it increases entropy. Your body is a local pocket of temporary order in a universe that is relentlessly moving toward disorder. You are fighting the heat death every second of your life, and you are losing. Not catastrophically, not quickly, not in any way that you can feel from moment to moment. But the same thermodynamic tide that will eventually swallow the stars is already lapping at you. The process we call aging is, at a fundamental level, the accumulation of entropy, the slow disordering of the molecular machinery that keeps you organized, the gradual failure of repair mechanisms that can't quite keep up with the constant wear, the buildup of damage that no living system can fully reverse. You are a temporary eddy in a current that runs only one way. And so is everything you've ever loved, everyone you've ever known, every building and bridge and painting and poem, every ecosystem and mountain range and ocean current, every civilization and religion and language and scientific theory, every record broken and every moment celebrated and every act of courage or kindness or genius. All of it, temporary. All of it, moving with the current. Does that disturb you? It should. But here's the thing. Here's the thing that physicists and philosophers and the small hours of the night eventually converge on. The temporariness doesn't make it meaningless. It might make it the opposite. Think about what it means that you are here right now, watching this, thinking these thoughts. You are alive during the Stelliferous Era, the age of stars, the bright chapter. Out of the unimaginable timeline that stretches from the Big Bang to the heat death, you exist right now, in the middle of the only period when the universe contains stars and planets and energy gradients and the conditions for life and thought and experience. In the incomprehensibly vast majority of the universe's existence, the dark eras, the black hole eras, the cold drifting final epoch, no life will exist. No experience will be possible. No questions will be asked. But right now, here, in this impossibly narrow slice of cosmic time, something extraordinarily unlikely is happening. Matter has organized itself into a being complex enough to look at the universe and ask what it is. You are a region of the cosmos that has folded back on itself and become aware. You are the universe knowing itself, and you exist during the only window in all of time when this is possible. That is not nothing. That is extraordinary. And yet there is a part of this that still sits wrong. A part that no amount of philosophical consolation fully quiets. Because it's not just that you will die, or that I will die, or that humanity will end. It's that everything will end. Every trace, every record, every effect of every cause set in motion since the beginning of time. In the final state of maximum entropy, there is no information, there is no memory, there is nothing stored anywhere that remembers anything that happened. The entire 13.8 billion year story of the universe, the Big Bang, the first stars, the supernovae that seeded space with the heavy elements that became planets, the oceans that formed on a small blue world, the first cell, the first eye, the first thought, the pyramids and the cathedrals and the space telescopes, and this moment right here. All of it will be gone. Not archived somewhere, not encoded in some other medium, not remembered by any mind anywhere. Gone, as if it never happened. And if that is true, if the end state of the universe contains no information whatsoever about what came before, then in what sense did any of it happen? Is the universe a story that will eventually be told to no one? A computation that runs to completion and then destroys its own output? These are not rhetorical questions. These are actual open problems in physics and philosophy. They have names. The information paradox, the Boltzmann brain problem, the disturbing possibility that in the incredibly vast span of time after the heat death, random quantum fluctuations might, with extraordinarily low probability, spontaneously assemble themselves into a conscious brain that exists briefly, having a single hallucinatory experience of apparent reality before dissolving back into chaos. If you live long enough, the math says it happens. Not soon, not predictably, but eventually, somewhere. The universe might briefly think again. It just won't know anything. Come back to now. Come back to the room you're sitting in, the light around you, the warmth of your own living body. You exist in a universe that is 13.8 billion years old. A universe that has spent the last several billion years producing increasingly complex structures, including, eventually, you. You are made of atoms that were forged in stellar furnaces, scattered by supernovae, drifting in molecular clouds for millions of years before gravity pulled them into a new solar system, a new planet, a new ocean, a new cell, a new organism, a new nervous system, and finally, here. Every atom in your body has its own cosmic history stretching back nearly to the Big Bang. You are not separate from the universe. You are the universe. And the universe, right now, in you, is aware. Outside your window, or wherever you are, whatever sky is above you, the galaxies are already moving. The space between the Milky Way and the Virgo cluster is stretching. The photons from the Andromeda galaxy, 2.5 million light-years away, and approaching us on a slow collision course that will play out at about 4 billion years, are crossing that void right now. The cosmic microwave background, the afterglow of the Big Bang, the faint radiation that fills all of space uniformly in every direction, is passing through you right now. Through your body, through your bones, through the exact space where your thoughts are forming. The echo of creation is inside you, always. And dark energy is at work, always. Not waiting, not dormant, active, stretching, growing. Every second, adding to the distances between galaxy clusters, accelerating the fabric of space, making the universe slightly larger, slightly colder, slightly more dilute. It doesn't take breaks. It doesn't slow down. While you sleep, while you work, while you love someone and while you grieve someone, and while you stand outside on a clear night and look up at the stars and feel small, dark energy is there, doing what it does, unstoppably. The universe is already dying. It started dying the moment it was born. The second law was in effect before the first second was up. Entropy was rising when the universe was a microsecond old. This is not a future event. It is not a far-off catastrophe. It is the condition of reality, the background state of existence. Everything is always in the process of becoming something simpler, something colder, something more dispersed, including the stars. There are roughly 2 trillion galaxies in the observable universe. 2 trillion, each containing, on average, hundreds of billions of stars. The number of stars currently burning in the universe exceeds the number of grains of sand on every beach of every ocean on Earth. Vastly exceeds it, and every single one of them is burning through a finite fuel supply. Every single one of them is moving, right now, toward its own ending. Some will explode and scatter their elements across space to seed new generations of stars. Some will collapse into neutron stars, spinning thousands of times per second, beaming radiation across the galaxy with lighthouse regularity. Some will collapse into black holes and spend trillions of years consuming whatever drifts into their gravity well. But all of them will be gone. The last red dwarf, the smallest, most fuel-efficient stars in the universe, the ones burning so slowly that their hydrogen supply will sustain them for 10 trillion years, will eventually exhaust its fuel and go cold. That will happen roughly 10 trillion years from now. And when it does, the Stelliferous Era will formally end. No announcement, no witness, no ceremony. A star dies, somewhere in a galaxy that contains no planets, no life, no observer. And the universe passes from one phase to the next, with no one there to notice. 10 trillion years. That sounds like a very long time. And on a human scale, on any biological scale, it is incomprehensible. But 10 trillion years is 10 to the 13th power. The death of the last white dwarf, 10 to the 78th power, is separated from that moment by a number that makes 10 trillion look like a rounding error. And the death of the last black hole, 10 to the 100th power, dwarfs even that. These are nested infinities of time, each one so much larger than the last that the previous scale simply ceases to matter. In the space between these milestones, in the dark eras of the universe's future, strange things might happen. At sufficiently vast timescales, quantum tunneling can produce outcomes that seem impossible on any shorter timeline. Protons might decay, if certain extensions of the Standard Model are correct, on timescales of around 10 to the 34th years. If they do, the composition of the universe changes fundamentally. No more atomic nuclei, no more conventional matter. Just electrons, positrons, neutrinos, photons, a universe of light and leptons drifting in the dark. Even stranger, if you wait long enough, so long that the timescale is not a number you can print, not a number that can be represented in any standard notation. Quantum fluctuations might spontaneously assemble an entire observable universe. Not our universe, not with our specific history. Just some configuration of matter and energy produced by pure chance out of the quantum foam. It would not last. It would not evolve into life. But it would, for a moment, exist. This is the Boltzmann brain problem taken to its logical extreme. This is what the late universe looks like to a physicist who follows the equations all the way to the end and doesn't flinch. This is where the math goes when you take seriously the proposition that the universe will persist, cold and empty and expanding, for an infinite duration. Even in perfect thermodynamic equilibrium, quantum mechanics doesn't shut off. The probability of fluctuations approaches zero, but approaches zero is not zero. And in infinite time, you can't escape the improbable. But we should come back to the near future, because there's something we haven't addressed yet. Something that changes the texture of everything we've been talking about. We are still in the bright chapter. The Stelliferous Era has roughly 1 trillion years left to run. The Sun has 5 billion years before it begins its death sequence. Life on Earth, if it survives its own tendency to create existential risks, has potentially billions of years of possible future ahead of it. The universe is not imminently ending. The darkness is not on our doorstep. And yet, it's coming. And the fact that it's coming, the fact that the same laws operating in your body right now are the laws that will eventually extinguish every last star, should change something about how you understand your existence, should change something about what it means to be alive right now, in this particular moment, on this particular world, in this particular chapter. Because here's the truth that all of this leads to. You are not an observer of the universe. You are not separate from it, watching it from outside. You are made of it, woven into it, participating in it. The energy flowing through you right now was forged in stellar explosions billions of years ago. The atoms that make your bones were inside other stars, other worlds, other organisms. The light that enters your eyes and becomes thought and memory and experience comes from a fusion reaction 93 million miles away that has been burning for 4.5 billion years. You are not a tiny thing happening in a big universe. You are the universe happening in one of its most improbable and temporary forms, a conscious one. And the scientists who study the end of everything, the cosmologists and astrophysicists who spend their careers staring down the barrel of entropy and mapping the death of time itself, they mostly aren't depressed by it. They are awed. They find in the immensity of the dying universe not nihilism, but perspective, not meaninglessness, but clarity. The end is real. The laws are absolute. And within those absolute laws, something extraordinary managed to happen anyway. Stars that never had to produce carbon produced carbon anyway. Planets that never had to develop oceans developed oceans anyway. Life that never had to emerge from chemistry emerged anyway. Minds that never had to form, that the laws of physics did not require and did not predict, formed anyway. You happened anyway. That is not small. That is the most remarkable thing in the universe. The latest measurement from Heino Falke's team, the one that revised the white dwarf timeline from 10 to the 1100th to 10 to the 78th. It made headlines because it shortened the timeline. But there's another way to read it. We looked at the end of the universe and measured it more carefully. We tightened the bounds. We made the math more precise. We, human beings, on a small planet, in a medium-sized galaxy, with brains made of atoms that were once inside dead stars, we calculated the death date of reality. That is something. In an indifferent universe of incomprehensible scale, we did something the universe did not do for itself. We understood it. We looked at our own finitude and the finitude of everything, and we made it a problem to be solved, instead of a mystery to be feared. We haven't solved it. We're still working on it. The dark energy question is still open. The false vacuum question is still open. The fate of information is still open. We don't know with certainty whether the universe will freeze or collapse, whether it will end quickly in a bubble of rewritten physics, or slowly in the last gasp of a black hole 10 to the 100th years from now. We are still in the middle of figuring it out, but we are figuring it out. A universe that produced beings capable of measuring its own death is not a universe that is merely dying. It is a universe that is, in some strange and brief and precious way, aware of its dying. Which means something is watching, and that something is you. Look up. If you can see the sky, look at it. If you're indoors, remember what it looks like. The darkness between the stars is not empty. It is full of radiation, full of dark energy, full of dark matter, full of virtual particles, full of gravitational waves from ancient collisions, full of neutrinos streaming through everything without stopping. The universe is not mostly stars and planets. Stars and planets make up less than 5% of the total energy content of the cosmos. 95% of everything that exists is invisible to us, unknown to us, still being figured out. We are in the first moments of understanding what we live in, and already we can see how it ends. Not in our lifetime. Not in the lifetime of humanity, probably. Not in the lifetime of the solar system, or the galaxy, or the age of stars, but with absolute mathematical certainty, guaranteed by laws that have not failed in 13.8 billion years and show no signs of failing now, it ends. The last star will go out. The last black hole will evaporate. The last particle will decay. The last fluctuation will settle into stillness, and the universe will be cold and dark and empty and silent and infinite and absolutely, perfectly, finally dead. That day is not today. Today there are stars. Today there is warmth and light and the wild improbability of life and the even wilder improbability of minds. Today you are here, made of stardust, carrying the universe's history inside your own body, capable of looking at the sky and understanding what you see. Today, the universe is still alive, and in the scale of what's coming, today lasts a very long time. But not forever. Nothing lasts forever, except the law that says so. Somewhere in the vast, cold, expanding dark between the galaxies, right now, at this exact moment, the last light from a dying star is crossing the void. It has been traveling for millions of years. It will travel for millions more. It will eventually reach the edge of what it can cross, outpaced by the expansion of the space it's moving through, frozen in transit, never arriving. A message sent from a fire that has long since gone cold, moving through the dark, toward nothing. That light is still moving. You will never see it. But it's there, and somewhere in the physics of its journey, in the equations that describe its path, the thermodynamics of its emission, the dark energy stretching the space it crosses, is everything you've just learned about where we are all going. The universe did not need you to understand this, but you do. And that, in a cosmos of 2 trillion galaxies and an expiration date measured in numbers that break human mathematics, that might be the strangest, rarest, most improbable thing that has ever happened. You always thought you were watching the universe, but the universe was watching itself, through you. And soon, it will forget.